Okay, some of you have noticed that as you suppose this is your 0 point, and you have started it here with a narrow Gaussian. Some of you have noticed that as it goes through the middle, it sort of widens. And then when it reaches here, it again becomes a narrow Gaussian, a mirror image of what it was in this side. And the question was, why does it sort of widen, fatten, when it comes to the middle? And some of you have played with the initial wave function, have noticed that if the initial wave function is fat, that means it is wider, then it becomes narrower here, and then again becomes wider here. So these are the things that you have already, some of you have already noticed. And I received a question regarding why does this happen. Now, apart from that, also this was a specific case of the harmonic oscillator wave function, harmonic oscillator V function. And if you take other V functions, you will similarly obtain various results which will excite your questions. And after this semester break, we will take up those questions. But this particular issue, I'll simply give you a hint. You see, your psi, whatever the psi was, psi at time t is equal to 0, that can be expressed as a linear combination of the initial stuff, right? So it is basically a sum over from n equal to 0 to infinity. There will be coefficients, say a n, and the psi different eigenfunctions as they evolve, okay? And it will be necessary that your a n mod square summed over should be equal to 1. That is the normalization necessity. And what are these psi n's? The psi n's, these were the psi n, small psi, these are the eigenfunctions of x only, times e to the power minus I e n t by h cos. Okay. And if e n is expanded, because you know what e n's are, it will be psi n x e to the power minus bracket 2n plus 1 by 2. This is I omega naught t. So now the initial wave function can be broken up into these kind of components, and some of these components are even functions and some of these components are odd functions. So we can write the psi x t as a sum of the even parts and the odd parts. I'll write it this way: even, it will be x and t, plus psi odd, again it will be x and t, right? Now, which are the the even parts and which are the odd parts? The psi even these are the ground ones, a naught, psi naught, uh, x e to the power, it will be minus I omega uh, t by 2. I was using omega naught, so naught plus this the second. First is distributed will be odd. Second is a2 psi 2 e to the power minus 5I omega naught t by 2, and so on and so forth. Similarly, the psi odd x and t will be the first one, a1 psi 1 x e to the power, this will be minus 3 I omega naught t by 2 plus a, this is going to be 3 psi 3 e to the power minus, it will be 7 I omega naught t by 2, and so on and so forth. So we can divide the initial wave function into the even part and the odd part. Now, if you take them separately, you will find that at t is equal to t by 2, if you put t is equal to t by 2, the even functions will behave one way and the odd functions will behave another way, and all the parts of the even functions will behave the same way. So, because e to the power minus I pi by 2 is the same as e to the power minus 5 I pi by 2. All these are equal to minus I. And similarly, e to the power minus 3 pi by 2 is equal to e to the power minus 7, I pi by 2. All this give you plus I. So using these, you will be able to figure out what happens to the even function and the odd function. Okay. And if you have the even function and the odd function, then you can add up to get the psi at x and capital T by 2. It will have two parts. I'll leave this to you. I'll not elaborate on this. So this is how you actually work out. And then you will see that if the initial wave function has both these parts, then after a time t by 2, it becomes exactly the same as what it was at time 0, only for minus x. So if you just work it out, you will find that this is the same as psi minus x 0, only there would be a factor minus I up front, which does not really matter because you are using mod psi square. So this implies that whatever the at time t0, whatever the wave function was at minus x, it will be the same at time t0, t by 2 at plus x. So this is something that you can easily calculate on your own and conclude that if at time t by 2 it was drawn that, if at time 0 it was here, at time t by 2 it was it will be exactly a mirror image of that, identical, only in the plus x direction. So that is what is expected from theory. But I would also, in addition, request you to calculate the standard deviation, the uncertainty. And not only uncertainty in x, but also the uncertainty in p. And if you do calculate that, I'm just giving a hint, I'm not doing the whole calculation again. If you do calculate that, you will find that because of the uncertainty principle, when the uncertainty in, it's a narrow Gaussian in x, which means that its uncertainty in x is small, which means at that time the uncertainty in p has to be large. So in this case, the uncertainty in p will be large, and again in this case the uncertainty in p will be large, x will be small. but the uncertainties also evolve in time. And if you actually do calculate that, you will find that they sort of evolve, uh, the uncertainties also evolve like a cosine function, increasing and decreasing. So the uncertainty in x will increase and decrease, uncertainty in p will increase and decrease, but with the condition that when the uncertainty in x is maximum, that in p should be minimum. Similarly, the uncertainty in p is maximum, then the x should be minimum. And since it sort of oscillates, then it goes without saying that if it is at 0 and it comes back to the same value here, in between the uncertainty in x will increase, uncertainty in p will decrease. So it will again oscillate like this, with the uncertainty in x minimum here, maximum here. Again it comes back, again it becomes maximum, again it's minimum. If you now, this will be interesting. If you now of the expectation value of x and p, then you can obtain something similar to a classical phase space description. So it will be something like this. But this is only the expectation value. Around that, there will be the uncertainties. So suppose you have started it with a very small uncertainty in x. So there will be large uncertainty in p. Now, if you plot an ellipse with the distance from the center as the uncertainty in x and p, then the uncertainty x is small here, uncertainty p is large here. So if you now plot it, it's something like this. Sorry, badly. It is something like this. So, so this sort of represents the uncertainty. It represents that the uncertainty is x is smaller, uncertainty p is larger. And when it comes here, it will rotate like this. When it comes here, you will find that it becomes something like this, which means the uncertainty in x is larger, p is smaller. Again, when it comes here, it will be like that. Again, when it comes here, it will be like this. And it will actually oscillate. So it does not only oscillate like this, but the difference between the classical harmonic oscillator and the quantum harmonic oscillator is that this is not a not a trajectory. We do not have any trajectory in quantum mechanics. What is happening is that this kind of a blob is going around, and the blob's shape changes as it goes around. Okay. This you can easily obtain if you just go back to the harmonic oscillator and calculate the uncertainties and the evolution of the uncertainties. Okay. By the way, what will happen if you started with a purely even function, like a purely even function, I mean the collection of these only, then the resulting psi will be an even function, something like this. I mean, it can be anything, but I mean, I'm not saying that it will be a nice Gaussian, but I'm just drawing that way. What will happen? Or if you take a wave function that is comprised only of the odd parts, then also it will be like this, because the mod square of the odd functions is also an even function. So if you have only either even or odd, then the result will be an even function. What will happen then? If you do that with your program that you have done, you will find that after some time it will become like this. That means it will spread. Again, it will become like that. So its spread will change and come back while its position will not move. The central position will not move. So it will appear as if it is breathing. So this kind of breathing you will see in the wave function. Interesting to see. So what I'll suggest is that you do this, and by that you sort of explore various possibilities regarding the various initial wave function, as well as after you have explored that, you do it with the different uh, v functions. The v functions would be, for example, if you have, if you consider a, this is the axis. In one part, it is nice quadratic. That means something like the harmonic oscillator V. But then it goes into a infinite well. That's a possibility. You can carry that out. You can do it with different other types of. For example, if you have this, and then you have got a small wall, what happens? And things like that. Well, I leave that to you, and you explore and have fun. Okay, now let us carry on what I wanted to do today. If there is there any question before we erase? Is there any question on what I did? No. Okay. Let's go ahead. All right. So far, everything that we did assumed that we know the state. That state can be a mixture of the eigenstates. That is possible. For example, a state can be psi, can be say 1 by root 2 psi naught plus 1 by root 2 psi 1. So that is a, still the state is known. It is a linear combination of various eigenstates, that's all right, but the state is known. So this is known. So this is known. That's important. We knew this, and we asked questions like, if I now make an observation of the energy, what is the likelihood that I'll get the energy corresponding to the ground state? What is the likelihood that I'll get energy corresponding to the first exercise state? What is the likelihood that if I observe the particle's position, it will be this? If I observe the particle's momentum, it will be that, and so on and so forth. All of that with the assumption that I know something. But there are situations where I don't. There are situations, in fact, more situations where we really do not have a clear idea about what the wave function is. By the way, a state like this is called a pure state, which means that it's there is no uncertainty regarding as far as the state is concerned. So this can be called a pure state. So pure state does not mean that it is just one eigenfunction. Pure state means I know for sure that the state is this, something like this. Okay. In general, I would, if I have to write it correctly, then I would not write only psi naught and psi 1. I would say that it is comprising a few things that includes the psi will be a combination of it will be a psi cns, then psi n's. No, what I'll do is I'll write it differently. It is a psi one possibility, Another possibility is psi 2, another possibility is psi 3, and so on and so forth, each with a probability. So the probability P1, probability P2, probability P3. So I do not know in which state it is. This state psi 1, psi 2, psi 3 can be a combination of various eigenstates. I don't care about that. Only thing is that there are a few possibilities and do not know in which state it is. But each state has a probability assigned to it. So it has a larger probability of being in psi 1, it's a smaller probability of being in psi 2, and so on and so forth. So the state then is given like this. When would you have that kind of a situation? For example, if you consider a situation where in this Stern-Gerlach experiment, the particles, the silver atoms, are coming out of the oven, but they have not yet been prepared in a particular state, which means that they have their angular momentum, spin angular momentum in the upward direction, z direction, could be anything, up or down. Both possibilities are there, and I don't know which possibility is there, but they have some probabilities assigned to be up, some probability assigned to be down. So similarly, so on and so forth. I mean, you can always imagine a large number of, say, electrons in a well, and each one, I don't know in which state it is, could be ground state, could be first excited state, could be second excited state, or could be some linear combination of these states. I don't know in which states these are, but they are. Now, if I make an observation of one of them, what am I likely to see? If I make an observation, say, of on the energy of a particle, which energy am I likely to see? Or what is the likelihood, what is the probability of seeing that particular energy value? So on and so forth, these kind of questions can arise. Now, the formalism normally used to answer questions like this, where we do not have an idea about the state it is in, but we have an idea about the possibilities and the probabilities assigned with each. Then there are ways of calculating the expectation values or the probabilities of each experimental outcome. And for that, we used something called the density matrix formalism. So this will be the topic of our discussion today. I'll start today, but maybe I'll have to finish after the break. So if I have a situation like this, a psi which is unknown, which is possible to have different psi 1, psi 2, psi 3, each with its probability, then we can write, of course, it will require that the P1 plus P2 plus P3 dot 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 should be equal to 1. That is the requirement, because it will be in any of one of the states. So this requirement is another hard requirement with which we have to proceed. Okay. So in order to start our progress into understanding density matrices, we will not start with this situation like this. Rather, we will start with one of these. Okay, say psi k, and we'll try to work out things for that, and then we'll consider mixed state like this. Okay. So first, let us understand what happens if we have a particular psi k. Okay. So the state vector then, I'm considering then a state vector psi. I'm not considering this situation right now. So let me delete this so that it does not confuse you. This is the setting in which the whole discussion is taking place. But right now I'll be considering a pure state. A pure state. Pure state means, again, let me clarify, that it need not be just an eigenstate. A pure state means where I know the state. It can be a linear combination of the states. So the pure state can be then written as psi t is equal to a summation over n Cn, and the this will be in general time dependent, and it will be uh, on some basis, and let us consider the eigen basis as un. So un are the eigen basis. So the state can be written in this form. That is something you know, and the the coefficient should satisfy the requirement that sum over n mod Cn square should be equal to 1. This is the normalization requirement. And the probability of seeing the energy value, a particular value will depend on the value of mod Cn square. And by the way, at this stage, let me clarify one thing. The mod Cn square is a probability of observing the nth state. So nth state means if it is a collection of energy eigenfunctions, the nth energy value. This is a kind of probability. But when I wrote that P1, psi 1, possibility P2, psi 2, this is another kind of probability. These two probabilities are different. Notice. This probability is a typical quantum mechanical probability because the state is composed of a linear combination of various eigen states, and therefore we have a quantum mechanical probability arising out of this. But these probabilities are classical probabilities. I have a state which may be in state psi 1 with probability P1. It may be in state psi 2 with probability P2. This is a classical probability. It is like, rolling a die, and it can have 1, 2, 3, 4, 5, 6 with some probabilities. So it's a similar situation. So these are classical probabilities, and these are quantum probabilities. So both kind of probabilities enter the picture here. Sorry. Now, let me write up front what the density matrix is. The density matrix is for this state. The density matrix is simply this. So you will say, oh, I will know that. This is something we know. We knew this related when these were the eigenstates, right? But in this case, we are constructing a similar thing, which is a projection operator, but in comprising these. So that is a density matrix, and we'll study the property of that matrix, and you'll find that that has a lot of characteristics, properties, which helps us a lot. So what are these? Firstly, consider A as an observable. So A is an observable. So A operator is the operator. So we are trying to find out what is the A matrix. This is something that you have already learned. Oh, sorry, operator. So you know that your A NM is to be obtained as in terms of the U's, which are the eigenbases, UN A operator UM. This is the ANM element of the operator. So if you have this, then you can try to obtain the expectation value of the observable A. If it is energy, what is the average energy? If it is a position, what is the average position? So on and so forth. So if A, you try to find out the expectation value, there's no reason to believe that it will be independent of time. So let me just write it so that it sits in your mind that it can be a function of time. So the expectation value. So this will be the expectation value of anything. We have already learned that it is the psi A psi. This is something you already know. And in this case, the psi's are actually psi t. Should I write so that it doesn't cause confusion later? So these are actually t and so these are time dependent psi's, okay, not eigen states, that stationary states. So you have this as the expectation value, and if you now break it up by using these, then first you will have to break this. Now this is the coefficient operating on the ket. Here it is the bra, so you will need to take the star of it. So it will become, there are two things. One is in this side and on this side. So I'll need to do two summations. One is with over N and M. So I'm just writing one summation sign. It will be Cn star will come out of this. There will be a Cn come out of this. So it is Cm coming out of this. And okay, let me again, for the sake of clarity of concept, put time dependence here, because this will be time dependent. And then what remains are the U, N, A, U, M, which we know to be the NM. So this is nothing but N, M, Cn star T, Cm T, and then this is the nth element of the A matrix. Okay. So it is immediately clear that the average value, the expectation value, if any observable, will be these two terms times the corresponding matrix element of the A matrix. And therefore, this term is very important, right? So this term in this case is very important. What is it? That is the issue. Now, we just said that the density matrix is this. So the density matrix so what are the matrix elements? The elements. The elements of any matrix are obtained as UM. Then that matrix was it was written as this. So it is psi t again psi t, and then un. So here is our matrix setting, operator setting, un, sandwich it. This gives the matrix element. Clear, this is something that we have learned long back, so we are comfortable with it. Now notice that then this is the psi n, psi t is component in the direction. So this will take out our cm t, and this is the, it is reversed. If it is un here and psi t here, it will give me cm. This will give you cm, un. It will give you cn, but now since it is opposite, it will give you cm star. I'm writing the star part first because we are used to writing, something star something. So it's just that. So this, what we tried to obtain here is actually here. Since which one is star, which one is, oh, sorry. We did do both as m. It will be Cn with a star, Cn with a star, Cm like that. Okay. And you notice that what sits here is nothing but the matrix element. Okay. So these are nothing but the matrix elements of the density matrix. It's called a rho. I'll give the sign. So these are the density matrix elements, and that immediately means that the expectation value of A is just the multiplication of the matrix elements of rho and A. So what we have concluded is that, let me write it so that it sort of sits in your class note. Rho mn equally a function of t. I'm always writing the t so that it gets into your head that these are functions of time. This will be un rho operator un, and that we obtain as Cn star t Cm. So this is very important relation, and you need to really remember that. So I will just underline it. These are the matrix elements of the density matrix. So what are the properties of this density matrix? Okay, we need to clear that out. So properties. What are the properties? Firstly, if it is a matrix, then we can calculate the trace. So the trace of the density matrix of rho will be each element. So trace is the summation of the diagonal elements where m and n are equal. So Cn star Cn and its summation over all n's. So it will be n. It is rho n t is equal to summation over n. It is C n t mod square, and this is obviously 1. So one important point is that the trace of the density matrix is always 1. This is a very important character, one problem. The second property is that we just calculated. Let me just uh, uh, write it in proper terms so that it sits in your mind. Any observable, if I want to calculate the expectation value, then we just obtain that it will be this. It is n comma m. It will be c n star t c m t a m n m. A n m. This is what we had obtained. Now, this is equal to sigma n comma m. These are, as you have already seen, these. So we can write it that way. It is um rho p un, and this is the matrix element, nth matrix element of A. So u n a u m, right? Now here is an identity summed over n, so we can take it out since we know that that is an identity. So it will only lead to one summation only over m. It is um. Now if this disappears, it is rho times a, rho a um, and since it is m summed over m, it is nothing but the trace of the matrix, which is rho t and matrix A. Okay, so you see the first advantage of this formalism. We have defined a specific matrix in terms of which the expectation value of any observable is very simple. All you need to do is to obtain that operator in matrix form, pre-multiply that by the density matrix and obtain the trace. That is the expectation value. Simple to calculate. So this is the property number 2, which is important. We need to remember. There is no space, so let me delete something up there. Now, let's start by writing it so that it remembers. So, rho t, it was, rho is an operator, is psi t psi. So, if this is the operator, then what about its rate of change? So, we'll take a derivative of it in order to explore what is the rate of change. So, rho t. There are two terms here, and therefore we have to take a derivative of each of them individually. First, we'll take a derivative of this. So, I'll put a bracket t of psi t and the bra plus the ket and then ddt of the bra. Now, this we know from the Schrodinger equation. this is nothing but 1 by I H cross uh, H operator operating on, it may be a time dependent operator, so let me keep that in mind, and operating on psi t. So this completes this part, and then we have psi t. Now, when we have to write this, so this part gets written, but when you when you have to calculate this, this is the ddt with the bra, not the ket. So we knew the ket's equation, and when we convert that into the bra equation, that 1 by I h cross will become minus 1 by I h cross. So it will be 1 by minus I h cross, and then it will be first this one psi t, and then it is psi t operated on from the right hand side by the Hamiltonian operator. Okay, so this is the way you would write the bra equation in the Schrodinger equation. So this immediately tells us that this is 1 by I h cross. This is h rho minus rho h. So it is nothing but the commutator of h and the rho. So this is the Schrodinger equation for, I can also cast it in the familiar form, I h cross d dt of rho. So this is the form of the differential. Sorry, this is the form of the differential equation that the density matrix will take. It looks very much like the usual Schrodinger equation. Only thing is that the right hand side is the commutator between the Hamiltonian as a matrix and your rho as a matrix. So you can easily compute that. So it's easy to compute this whole thing. You would notice that this formalism is leading to certain advantages as far as the computation is concerned, and as we will see, so far we are dealing with pure states. Even in pure states, we begin to see the advantages, and when it comes to mixed state, where we really do not know exactly which state it is in, its advantage will be even more prominent. But I probably do not have time to get into that today. I'll do that next day. Let me, with the time that I have, do something. This I want to keep. All right. So what is the probability now? What is the probability of observing the eigenvalue an? In the observable A that we have discussed now, the eigenvalues are an. So if you really make an observation, you can only observe any of the A1, A2, A3, A4 and all that. So what is the probability of observing a particular eigenvalue, an? So it is probability of an. This we know is the an, this is the eigenvector psi. Uh, Psi is overlap on the eigenvector. It's mod. That is the probability, right? And this can be expanded as I mean this star, this, and this star is psi can be put in this side, so I can write it as psi an psi, right? This is the star part of it, and this is the probability amplitude and the probability amplitude star, so that gives the Morse aspect. So you have this expression, and this is something that we know. This is the projection operator onto the eigenvector an. Let's call it Pn. So this is the projection operator. So if it is a projection operator, then we can see that this can be written as your psi in operator psi. Just replace it. So this is again the way it has been written. You can see that this is nothing but the expectation value of Pn. This is psi, I mean bracketing the operator is the expectation value of the operator. So this expectation value of okay. And we have already seen that if you want to calculate the expectation value of anything in the density matrix formalism, then this can be written as trace of that operator and the density matrix. We've just learned that, right? So we have just applied that. So the probability of obtaining an eigenvalue an is simply obtained as by multiplying that projection operator with the density matrix and then obtaining the trace of it. So we have written two of the properties. This is the third property. Okay. I don't think we have any more time to continue. It's about 4 minutes left. So let's finish. Let's stop today. Is there any question? Then I'll answer. Today I could only proceed with the pure state and what density matrices mean for these. And we'll then go with that idea into the mixed states.